Hello everyone! Today we will cover section 4 in chapter 7 and we will also cover part of section 5. So first, electron configurations of ions. We did electron configurations of atoms earlier, so now we can apply what we've learned to ions. So first of all, you already know from our earlier work that anions have negative charges, and we obtain anions by adding electrons. So we add one or more electrons, and the number of electrons we add will be determined by the electron configuration of the next noble gas in the periodic table. So in the past you had to memorize this, but now you don't. You can figure this out by looking at the position of the element in the periodic table and trying to see which next noble gas there is. For cations, it's the opposite. So what we do here is we remove electrons, and since electrons are negatively charged, when we remove an electron, we get a positive ion, and we'll do the same thing here, is that we will remove one or more valence electrons to get to the next noble gas electron configuration. For cations, we usually remove electrons of the highest value of n. That might not be the highest energy, but that's how the electrons are lost. So we need to keep that in mind. So let's start with lithium like we did the last time. So lithium has 3 electrons total. It has 2 in the 1s orbital and 1 in the 2s orbital. So we write the electron configuration as 1s2, 2s1. When we learned how to do this, we learned that we could write a shorthand notation where we, instead of writing out the whole electron configuration like we do here, that we could use a shorthand notation where we noted that lithium's electron configuration was the same as helium's with 1 extra 2s1 electron. So lithium is a metal. It's on the left side of the periodic table. You remember that metals lose electrons to form cations, so that's the electron that's lost. So if lithium loses that 2s1 electron, now its electron configuration is the same as helium's. So that gives lithium a Li plus charge, and it gives it the same configuration as helium. So remember when we first introduced the idea of the electron configurations and writing these shorthand, we noticed for lithium that the 1s2 electrons were the core electrons. So the core electrons were the same as the electrons that represented the electron configuration for helium. And then the 2s1 electron was in addition to that, and we called those valence electrons. So what happens here is that lithium loses its valence electron. It has only 1, and when it loses that, it becomes an Li plus cation. So if we extend this to what we learned in group 1A, we find that if I remind you of all of the electron configurations that we could draw for all of the 1A atoms in the periodic table, you can see that each one of them has valence electrons. They each all have 1, and the 1 electron is 1 electron above and beyond what it would have in the noble gas configuration. So in our book, our authors write a little equation where here they don't write they do write the whole electron configuration. They don't use the noble gas configuration. But they notice that if you take sodium and then you lose that 3s1 electron, then what you get is a positive sodium ion, and there's the negatively charged electron that's lost. And now you have an electron configuration that's the same as neon. So that means all of them will do this. So lithium, sodium, potassium, rubidium, cesium, and francium all will lose that 1 valence electron, and now their electron configuration is the same as a noble gas. So again, that's something that you memorized before, but now you don't have to. So you can just look at the electron configuration and you can easily predict that all of the elements in group 1A would lose 1 valence electron to form +1 cations. Okay, so continuing on with group 2A, so we did the same thing with beryllium, where we learned we could draw the electron configuration as helium 2s2. So we'll do the same thing here, except here we're losing 2 electrons. So again, beryllium, magnesium, calcium, strontium, barium, and radium will all lose those s electrons, those 2 s electrons, and now they have electron configurations that are the same as noble gases. So all of the metals in group 2A will lose 2 electrons to become plus 2 cations. Let's go on to group 3A. Now this gets a little trickier. I did actually notice that I had simplified things maybe a little bit too much the last time when I was doing electron configurations for you. So this is trickier because at the top of the group you have non-metals or maybe metalloids, and then you have metals more as you get down to the bottom. But here we are going to lose 3 valence electrons. So here we have sufficient metal character that these atoms are going to lose electrons. So here we have 2s2, 2p1 in the case of boron. And again, all of these elements here also have 2 s electrons and 1 p electron. Now, when we get down a little farther, you can see that gallium, indium, they have d electrons, but those are full and they're not considered to be valence electrons. So what I did here is I highlighted in red the electrons that were considered to be valence electrons. And down here with thallium, it has again, a filled F orbital. So it has 4F14, so all of that's filled. So again, that's not considered to be valence electrons either. So what happens is that you would generally predict for boron and aluminum and gallium that you'll lose those 3 valence electrons, the 2 s electrons and the 1 p electron. But indium could actually lose just the p electron and keep those 5 s's. After all, it's a filled shell. Or you might have indium 3+ where it does lose those 5 s electrons. So it's possible to have indium +1 and indium +3. And the same thing for thallium. The thallium can lose that 6p electron and keep its 2 6s electrons, or it could lose both the p and the s, and then it becomes thallium 3+. So now we can use electron configurations to explain why some elements have the capability of having more than one oxidation state. So I didn't write here, this is the group 4A, and again, we're definitely getting trickier here because carbon is a nonmetal, silicon is a metalloid, and so is germanium. But when we get to tin and lead, we definitely have metals down at the bottom there. So I didn't write the original electron configurations because I didn't have room on the slide. But we can see with carbon, if we lose 4 electrons, so here the carbon and the silicon, the way that I have drawn them, they've lost their 4 valence electrons. They lost 2 p electrons and 2 s electrons. But they can also gain because you're trying to get to be a noble gas and you're kind of halfway in between. So carbon could lose 4 to become like helium, or can gain 4 to look like neon. Same thing with silicon. It can lose 4 to become like neon, or gain 4 to become like argon. Now, we should note that carbon and silicon are more likely to share electrons rather than to transfer them, in which case these oxidation numbers just become bookkeeping. And we've seen that in the past with some of the earlier work that we did earlier in the semester. But if we're getting down here with germanium and tin and lead, again, we can see that we have the possibility of having 2 different oxidation states, either +2 or +4. So here the germanium has lost its p electrons, but not its s. And here, if it becomes 4+, it's lost both the p and the s electrons. And the same thing for the tin and the lead. So here again, we can see why it's possible for germanium, tin, and lead to have 2 different oxidation states. And the authors of our book show us how germanium could lose the 2 4p electrons to form Ge2+. But what they don't show us that it is possible for germanium to lose those 4s electrons as well, in which case it would become Ge4+. Okay, so now we're past the halfway point. So we're in 5A. So here I decided to focus on nitrogen, phosphorus. This is arsenic and antimony. So nitrogen and phosphorus are nonmetals. And then we know that nonmetals gain electrons. So here, if we look at 2s2, 2p3, or 3s2, 3p3, that we have 5 valence electrons. So it is easier to gain 3 than to lose 5, although you could. And that's going to be true with the metals down here. But the nitrogen and the phosphorus can gain 3 electrons. So here, nitrogen would go from 2s2, 2p3 to 2s2, 2p6, in which case it's N3 minus. Phosphorus can go from 3s2, 3p6, and then now its electron configuration is like argon. But remember, metals lose. So nonmetals gain and metals lose generally. So if we look at arsenic, again, let's ignore the D's because they're all full. So arsenic can lose those 4p electrons to become As3 plus, or it can lose the S's as well, and then it becomes As5 plus. And the antimony the same way. It can lose just those 3p electrons to form sp3 plus, or it can lose all 5 to form sp5 plus. What about group 6? So here I've decided to focus just on the nonmetals. So nonmetals gain generally. So here, if I have oxygen and sulfur, you can see that if I gain 2 electrons, oxygen will go from helium 2s2 2p6, which means it's an O2 minus, and now it looks like neon. Whereas sulfur is 3s2 3p4. It can gain 2 to form 3s2 3p6, which makes it look like argon. And the same thing with selenium. It can, again, let's ignore the D's because they're all full, but it can go from 4s2 4p4 to 4s2 4p6, and then that looks like krypton. So here, our group 6A atoms that have 6 valence electrons have gained 2 to attain the electron configuration of a noble gas. So our authors of our book illustrate this here. They write out the complete electron configuration for sulfur and then show that if we have 3p4, if you gain 2 electrons, then you become from sulfur to sulfide, and now you have this 1s2, 2s2, 2p6, 3s2, 3p6, which looks like argon. So group 7A, so I've decided to focus on these halogens right here because we work with them in lab. So fluorine, chlorine, bromine, and iodine, they all have 7 valence electrons. So here it's a simple matter to gain 1, and now fluorine looks like neon, fluoride looks like neon, chloride looks like argon, bromide looks like krypton, and iodide looks like xenon. And the authors of our book show us this here too, or for fluorine. They show 1s2, 2s2, 2p5. You gain 1 electron, and now everything's full. 1s2, 2s2, 2p6, and that looks like neon. So for the transition elements, things get a little trickier, but again, we can use electron configurations to explain, again, why some of these transition elements, just like some of the metals over on the right side of the periodic table, have variable oxidation states. So I made you memorize iron can form Fe2 plus or Fe3 plus, so now we can see how it works. So if iron loses those 4s2 electrons, then its electron configuration becomes argon plus 3d6. And now we have a Fe2 plus ion. So we should note for the transition metals that the 2s electrons are lost first. So that wasn't true in the main group metals I just showed you. So we lose the s electrons first. To form Fe3 plus, the reason we get that is because you lose the 4s2 electrons and you have 3d6. If you lose 1 more, then you become 3d5. And 3d5 is half full. And remember, we learned before that full orbitals are stable, but half full orbitals are stable too. So losing just 1 more gives you a 3d5, which is half full and stable. So that leads pretty logically, I think, into a discussion of diamagnetism and paramagnetism. So elements and compounds that have unpaired electrons are attracted to magnets, and those species are said to be paramagnetic. But if all of the electrons are paired with opposite spins, of course, because that's how we do it, they experience a slight repulsion when subjected to a magnetic field, and we say that these substances are diamagnetic. So this is a picture from our book, and this shows that if we have a sample in a glass tube and we put it in the presence of a magnet, so here the magnet is off, but if we turn the magnet on, then we can actually notice from here, because our little balance here tips. So this tells us the degree of paramagnetism. This might be a little bit easier to see right here, where we can see that if we have a sample of iron 3 oxide, and then here the magnet's turned off. But if we turn the magnet on, we can see we can hold up a magnet to it, and we can see that our iron 3 oxide actually is attracted to the magnet. So we can explain that. Again, if we look at iron 3 plus, remember I just showed you that iron 3 plus, you lose 4s electrons and you lose one of the d's, and then now you have a 3d5, so you have all 5 unpaired electrons. So this explains why iron 3 plus is paramagnetic, because it has unpaired electrons. So there's an example in our book that asks us, look at copper, copper plus, and copper 2 plus, and we need to use electron configurations and then draw these orbital box diagrams to answer this question. So here for copper, it's 3d10 4s1. So this is one of those exceptions. If you were writing the electron configuration based on the periodic table, you might say 4s2 3d9. But what we do is we take one of those electrons out of the 4s and we put it into the d's, because that way we get this nice filled 3d orbital. But you notice we do have one unpaired electron in the 4s, so copper by itself is paramagnetic. What if we have copper plus 1? Well, if we have copper plus 1, we take away that electron, and now we're just left with argon 3d10. So now everybody's full. So everybody is full and everybody is paired. There are no unpaired electrons, and copper plus is diamagnetic. Well, what about if we have copper 2 plus? Well, if we do that, then we notice that we took away both of those electrons in the 4s, and now this gives us 3d9. So most of these are paired, but we still have one unpaired electron right here, and that's enough to make this thing paramagnetic. So copper 2 plus has one unpaired electron and is paramagnetic. So we should note that paramagnetism and ferromagnetism is different. So we have more experience in everyday life with ferromagnetism. So here this shows submagnets. Maybe you played with something like this. There's some nice childhood toys that are magnets. So that's ferromagnetism. And in ferromagnetism, this book picture from our book explains it fairly well. I think that here the spins of the unpaired electrons all align themselves in the same direction. And they do that even if you don't apply a magnetic field to them. Whereas what we were just showing here is that if we have these unpaired electrons without a magnetic field, then the unpaired electrons are randomly oriented. But as soon as we apply that magnetic field, then the spins become aligned. So in terms of the strength of magnetism, ferromagnetism is much stronger than paramagnetism, because with ferromagnetism, the spins are aligned even in the absence of the application of a magnetic field. But for paramagnetism, you have to actually apply an external magnetic field. Okay, so let's go on to section 5. We won't cover all of it today because it's very extensive, but we'll get started. So again, we're going to use our knowledge of electron configurations. So once we understand those, then you can use them to learn that there are similarities in elemental properties as the result of these configurations. So let's use those to look at physical and chemical properties. And what we notice is that the periodic table is a wonderful tool because these properties change in a predictable way when you're moving down groups and across periods. So we want to be able to make those predictions. So let's talk about atomic radius first. Okay, so atomic radius first. So atomic radius just tells us, well, what's the size of the electron in the outermost orbital? So this picture from our book shows us that if we go down a group, so here's 1A, if we go down a group, notice starting from hydrogen and going all the way down to cesium, that the atomic size increases. But say, look if we look at say the second period or the third period. As we go across the period, though, the size decreases. So we want to understand why that's true. Okay, so first, if I'm just looking at atomic size, and here I picked group 1A, if we go down a group, we can see that the atomic radius gets larger. And we can understand this by, again, referring to electron configurations. So if we see where we are, for hydrogen, this would be 1s1, 2s1, 1s1, 2s1, 3s1, 4s1, 5s1, 6s1. So as we're going down the group, we're increasing the value of the principal quantum number n. So we're here with cesium, you have its last electron is in a 6s orbital, whereas for hydrogen, it's just in a 1s orbital. So the larger the value of n, the farther away you are in the nucleus. And since we're measuring atomic radius by how far away that last electron is, then cesium will have a much larger atomic radius than hydrogen. So it gets a little trickier if you go across a period. So going across a period, the value of n stays the same. So if we look over here with sodium and magnesium, so this is 3s1, 3s2, but then we have 3p1, 3p2, 3p3, 3p4, 3p5, and then we would have 3p6 if they showed us the noble gas. So we are going across the period. The value of n stays the same. So here we're still looking at whether it's 3s or 3p, where the value of n is the same. But the other thing that happens is the number of protons increases. So as you go across the period, the number of electrons added to the nucleus gets larger. So that means if you have, as you go across, a greater and greater number of protons, and the electrons are in orbitals with the same n, what happens is you have a greater Coulombic force of attraction between the nucleus and the valence electrons. So that sort of pulls the electrons in closer to the nucleus, and the atomic radius decreases. So here we can use the concept of effective nuclear charge to explain this. And that was covered earlier in the chapter, and you might remember that I skipped it because I thought it made more sense to talk about it here. So what is effective nuclear charge? Well, our authors use Z star to represent effective nuclear charge. And that is the net charge experienced by an electron resulting from the balance of attractive forces of the nucleus and the repulsive forces of the other electrons. So here, let's use lithium as our example again. So again, lithium has an electron configuration of 1s2, 2s1. So in our discussion, let us focus on 2s1. So let's look at just that electron. So that outermost electron experiences an attractive force from the nucleus. So remember, lithium has 3 protons, and each proton has a +1 charge. So we would say its nucleus has a charge of +3. So that outermost electron is attracted to the nucleus, but it experiences a repulsive force from the other 2 electrons, because these 1s2 electrons right here, they're negatively charged, just like the 2s1 electron is. So it's repelled by those other 2. So if we were to calculate a net effective nuclear charge, we would say +1, because this electron is attracted to the 3 protons on the nucleus and it's repelled by those other two electrons. So +3 and -2 is +1. So that seems kind of simple, and it is, and we need to modify this a little bit because the electrons don't really experience the full +3 charge of the nucleus. And they don't because those 1s electrons screen that 2s electron from experiencing that full positive charge. So we can illustrate that by looking at this figure right here. So these peaks right here map the probability distribution for the 1s and the 2s electrons. So if you look in this picture right here, see where everything is shaded? That is, from this distance right here, that is the probability distribution for those 1s electrons. And this is lithium, so we have got 2 of them. But then if we look at this peak right here, that's the probability distribution for the 2s electron, and you notice that there's a little bit of overlap with this peak. This peak kind of strays into that area where we find the 1s electron. So what has happened is if we look at that overlap, that means the probability distribution for the 2s electron penetrates the peak for the 1s orbital. So that means if the probability distribution, if the electron just happens to find itself at any given moment in this region over here, it is actually closer to the nucleus, and the 1s electrons don't screen it all that much. So what happens is the effective nuclear charge is going to be a little bit greater. So it's not +1, it's more like +1.28 because the 1s electrons aren't screening it as much as it would be if it was way out here. So anyway, that explains why the effective nuclear charge isn't exactly +1. It's actually a little higher than that. So we can actually measure this, this effective nuclear charge. And here on this graph, this blue line just shows the atomic number. So remember, the atomic number just means the number of protons. And if we start with hydrogen, we have 1 proton, and if we go all the way up to argon, we've got 18. So we're plotting the number of protons from 1 to 18. And then in green, we look at this screening constant to see how well the inner shell electrons screen the outer ones. And we can come up with this effective nuclear charge right here. So you notice it's a little bit lower than the atomic number. So if I just focus here on lithium, and I want to go from lithium to neon, I'm going across the second period, and there's this really nice line right here that shows that as you go from lithium to neon, the effective nuclear charge increases. So that's why neon is going to be smaller than lithium, because the number of protons goes up, the effective nuclear charge goes up. That means those electrons are being drawn in to the nucleus much more closely, and because of the penetration of those orbitals, those outermost electrons are experiencing a greater effective nuclear charge than you think that they might. Then that explains that size decrease as you go across the period. So to summarize, so effective nuclear charge, so our authors call it Z star, or sometimes you see it as ZF for effective nuclear charge. So the effective nuclear charge increases across a period, and again, you're adding electrons in the same shell, but the number of protons goes up. So we should note that electrons in the same energy level shield each other to some extent, but in the inner energy levels, they shield the outer electrons very effectively. So that means the further from the nucleus an electron is, the lower the effective nuclear charge is for that particular electron. Okay, so that was a discussion of atomic size and why when you go down a group, the size gets bigger, and why you go across a period, the size gets smaller. So atomic size increases as you go down a group because you're adding energy levels. Atomic size decreases across a period because of the increase in the effective nuclear charge. Okay, so let's look at another periodic trend, and this is called ionization energy. So that's the energy required to remove an electron from an atom. So since you have to put energy in order to remove an electron from an atom, when you measure ionization energy, they always have positive values. So remember we learned in chapter 5, when you have to put energy in, the value is going to be positive. So if you're going to remove an electron from an atom, remember that electron is attracted to the nucleus, so you have to put energy in to overcome that attraction to be able to remove the electron from the atom. So it makes sense, I think, that ionization energy is generally higher for electrons closer to the nucleus. So closer to the nucleus, you have a greater effective nuclear charge. You experience more of that attractive force from the nucleus. So that means it's going to be more difficult to remove an electron from that atom. So the ionization energy trend, so again, if we're looking just at main group right now, so we're not going to discuss the transition elements. So for the S and the P block elements, ionization energy generally increases across a period and decreases down a group. So again, we can explain the trend across the period because the effective nuclear charge increases when you increase the atomic number. So as the effective nuclear charge increases, that means that the energy required to remove an electron increases because that outermost electron is experiencing a greater attractive force from the nucleus. Going down a group, though, the ionization energy decreases because here you're not in the same value of n. Here you're adding electrons to higher values of n. So those electrons become farther and farther and farther away from the nucleus. They don't have a great attraction for the nucleus. They're held far less strongly, and it's much easier to remove them. So if we look at this table right here, so let's go down a group first. So if I look here with lithium, and we're just going to look at first ionization energy. So that means how much energy does it take us to remove one electron? So for the first electron for lithium, 513 kilojoules per mole. For sodium, it's 496 kilojoules per mole, and for potassium, it's 419 kilojoules per mole. So you notice as we go down the group, when we go from the second period where that first electron would be a 2s1, this is a 3s1, that's a 4s1. So these electrons are getting farther and farther away from the nucleus. So it's much easier to pull off the electron from the potassium than it is from the lithium. And we can see that we have periodic trends that are similar. So for beryllium, again, 899 for the first electron, and then 738 for the second, and 590. So you can see if you're going to go down any of these groups, you can see that the first ionization energies get lower. Now, if you go across a group, so here let's look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So here, there are some exceptions, and I'll tell you about that in a minute. But in general, as you go across, we go from 513, 899. Well, here we drop a little bit, so that's an exception. 1086, 1402. Okay, here's another exception, 1314, 1681, 2080 kilojoules per mole. So there are a couple exceptions, but in general, as you go across the period, the ionization energy gets larger. So here, if I'm in the second period, these are 2s1 electrons right here, and these are 2p, I'm not drawing this very well, 2p electrons right here. So again, you're in the same value of n, but adding protons, so the effective nuclear charge is increasing. So as you go across, it gets more and more difficult for that last electron to be removed. So this is a nice visual right here. So again, if I'm going to use my lithium to nitrogen, if I look at this blue right here, and in general, from lithium to neon, the ionization energy does go up. But you can see a couple of exceptions. So boron and oxygen are the two exceptions. So if we look at boron, what you're doing right here is you would be removing a 2s electron, and here you're removing a 2s. But for boron, you'd be removing a 2p electron. So, so again, there's going to be more shielding. from the 2s electron, so it's going to be easier to remove that 2p electron. But then the trend goes up again, so you're removing 2p1, 2p2, 2p3. Now this goes down because this would be 2p4, and if you remove one electron, then you're back to 2p3, and that's half filled. So so removing that fourth 2p electron from oxygen is a little bit easier because it gives you that nice stable half-filled 2p3 subshell. And then again, if you go from fluorine to neon, then the trend continues. So there are some exceptions, and you can see where the exceptions are, and they're in the same places for the other groups, but you can see in general the trend increase as you go across a period. And again, it's because of the effective nuclear charge increasing as you add more protons and the shielding of those inner shell electrons that these electrons are experiencing. So the other thing we can do is we can look at not just first ionization energies, but second and third. And this is going to be different depending on what element you're looking at. So our authors look at magnesium. So the ionization energies, this is the first ionization energy. So what we're going to be doing, if you look at the electron configuration for magnesium, you're removing one of those 3s electrons. So we can measure this. This is 738 kilojoules per mole. So that's the least tightly held and easiest to remove. So now we have an Mg plus ion, and we have removed one electron. So the second ionization energy, what happens is this is going to be more difficult because now you're removing an electron from a positively charged ion, and that's more difficult to do. So this second ionization energy is going to be a little greater. But now we have Mg2 plus, and now we have an electron configuration that looks like let me look at my periodic table. It looks like neon. So that's going to be a stable noble gas electron configuration, which means then if I try and pull off a third electron, so notice I'm at 1,451 kilojoules per mole, there's a huge jump in the ionization energy if I try and pull off a third one, because here I've got the Mg2 plus with its electron configuration that looks like neon, whereas now I'm trying to break that up, and that's going to take way, way more energy. So removing an electron from a full shell is going to be especially difficult. And again, it has to do with the effective nuclear charge, and you're trying here again to remove an electron from a positively charged ion. So we're going to stop there with this section 5, and there are more periodic trends that we can discuss that are based on electron configuration. So we will pick those up next time. But in the meantime, you should test your ability to understand these concepts by doing the following problems. So I hope you enjoyed this lecture on periodic trends, and I will see you next time.